Okay, so let's talk about the operations that you can do with vectors. So the first and easiest is multiplying by a scalar, meaning a number. Okay, so scalar multiplication involves the product of a vector and a scalar. So each component of the vector is multiplied by the scalar. So if you have a vector v and a number k, so I'm talking like 3, -7, 1.2, something like that. A scalar times a vector, you just multiply each of the vector components by that scalar. Okay. Only the magnitude changes, unless if k is negative, then the vector is going to reverse direction. You can imagine if we're multiplying by a negative number, if it's pointing this way, it's going to flip and point the other direction. So let's practice. If we have a vector and it has components 3, 1, find 3 times v, 1/2 times v, and -v. All right, 3 times v, we just multiply, we get 9, 3. 1/2 v, we get 3/2, 1/2. -v, we get -3, -1. Okay, so really not anything tricky going on here. And we can see what happens to them graphically. If this is our original vector v, then multiplying it by 3 makes it 3 times as long. The direction stays the same, but the magnitude increases by 3. 1/2 makes it half as long, same direction. -v, the magnitude is the same, but it has flipped and is pointing the other direction. Okay. What about addition and subtraction? All right, so we can think about this graphically. And if we have a vector u, let's talk about this one first. Here's our u, and here's our vector v. And notice we have, this is the initial and terminal, and here's our arrow. Initial and terminal, here's our arrow. We call this tail to tip. Okay, so if we're adding vectors together, graphically we can think about this as here's our first vector, and then we move the other vector. Remember, we can move them around anywhere we want in the plane. We move the other vector so that its tail is touching the tip of the first vector. And we could add a bunch of vectors together and just keep doing this. Okay, we move them around tail to tip, and then connect them from the initial point to the final point, the final arrow. That is graphically, and that's what happens when we add them. Okay, those are going to be our numbers. U plus v is going to be this vector here, and we'll do it algebraically in just a minute. What if we had, so u, same vector u here. Okay, here's our u. We just have moved it over. And now instead we have minus v. Okay, so v, remember v used to go this way, and now we have a minus v. We've flipped the direction. U minus v is going to be that way. Okay, we start at the initial point and end at the terminal point of the tail to tip, putting them together. So subtraction, really, I mean, we could just think of this as adding -v, right? Just like we do with numbers. Here's another geometric depiction of this. If we have u plus v, we can kind of think of this as a parallelogram, right? And that would be the diagonal. And if instead we were subtracting, here's u, remember, same parallelogram, these two sides are the same length, minus v is going to go this direction, then u minus v is the other diagonal. That's just a geometric way to think about it. Algebraically, this is not tricky. Okay, so if we have u and v, if we want to add them together, you literally just add the x components and add the y components. Okay, so 3 plus -1, -2 plus 4, we get 2, 2. And we can graphically see this. Here's 3, -2. And here's -1, 4. We've moved v so that we are lining these up tail to tip. Right, here's our first vector and our second vector. Connecting from the initial to the terminal point there is u plus v, and sure enough, it's 2, 2. U minus v is just u plus minus v. So 3 minus 2, we're going to just say, okay, that's going to be 3 minus -1, and -2 minus or plus -4. And we're going to get 4, -6. Here's our vector u. Here's minus v. And u minus v is going to be 4, -6, this vector here. Okay, so nothing tricky, just add or subtract the components. So what if you kind of combine these into a problem and you said, here's u, here's v, find 3u plus 2v. So first thing, you just would find 3u by multiplying by a scalar. You can obviously pause this and look at the numbers. W, now you're going to add these two together. So 9 minus 2 is going to give us 7. -6 plus 8 equals 2. All right, so sometimes we're going to break vectors up. well, I mean, we've already kind of been doing this into their components, their x component and y component, okay? We're going to do this more formally and write vectors like this, a times I plus b times j. So I, we're imagining, is a vector that is just magnitude 1 that goes along the x-axis, and j is a unit vector that goes along the y-axis, okay? So this is really not any harder than writing this in component form like AB. Okay, we're just writing it as a times I plus b times j. So here's the vector a times I, here's the vector b times j, and this would be the sum of those two vectors, right? They're tail to tip, and then the sum would be the hypotenuse of that triangle, just as if we were writing this in component form AB. Okay, so this isn't like a big new concept, it's just a different way to write this. So if we have an initial point, terminal point, we want to write it in terms of I and j. They're saying find the position vector. So just like we did before, we'd say the terminal minus initial, so -6 minus 2 gives us -8. 6 minus -6 gives us 12. And instead of writing square bracket or kind of pointed bracket -8, 12, we write -8i plus 12j. The last operation that we can do with vectors is a dot product. Okay, so this is like kind of like multiplying them together, but not exactly. If we have, and we're not really even going to use this as an application. I just wanted you to see this. You'll take dot products in future classes, but I just wanted you to see how this works. If you have a vector v and a vector u, and you have a dot product between them, all you do is you're going to get a number. So a times c plus b times d. So you're going to get, you take a dot product, you don't get a vector, you get a number. So the dot product between this vector v and this vector u, so we multiply 5 times -3, and we multiply 12 and 4, and we add those two numbers together, and we get a dot product of 33. And that's the answer. We're not going to interpret it or use it for anything in this class. I'm going to ask you to try it a few times. It's pretty algebraically pretty straightforward. In future classes, when you're dealing with vectors more, you'll use dot products. I just wanted you to see it. We're not going to do anything tricky with it here. You just multiply the first two numbers plus multiply the last two numbers. There you go. That's your dot product between two vectors. Okay, you can use it eventually to find things like the angle between two vectors, but we're not going to worry about that this semester. So let me know if you have any questions.